Welcome to section 4.2. So we're going to continue our discussion of vector spaces by talking about a couple of specific vector spaces that are really important in terms of matrices. These are null spaces, column spaces, row spaces, and we'll also talk about how this affects linear transformations. So let's just kind of jump in. We're going to break into some review because actually this is going to hit. We mentioned the four fundamental spaces of a matrix, and we'll talk about examples of finding a subspace. So as a quick review, a linear combination is if I have a set of vectors. Remember, vectors don't have to be in the traditional sense. They can just be anything in a vector space. A linear combination is a sum of scalar multiples of each of those vectors. So with that in mind, what are some of the ways we can use linear combinations? Well, remember, if we have a homogeneous system, the system is homogeneous if we're talking about if it can be written AX equals 0. Well, the solutions, remember we solved this doing row operations, but this also gave us general solutions, which actually made up, believe it or not, a vector space that was a linear combination. So the answer always looked like, and I'll get to this, remember the answer looked like a set of vectors with constants being multiplied. So if we have this, and when we want to set this up where you're solving this, just a quick reminder, how would you do that? Well, we make this matrix here and we do a row reduction. So I'll let you just remind yourself by pausing the video and go ahead and reduce said matrix. All right, now hopefully you did that. And if you did it, some of the row operations you should have ended up with this. You could have swapped, by the way, rows 1 and 2, and then I can add and do all sorts of other fun stuff like that. So if you didn't get this, go back and check your work. I'll skip all the details at this point in time because we've done a lot of row reduction. If you still have questions and are totally confused, you're welcome to reach out to me. But if I have this as reduced, let's just jump to this point in time. What does this tell me about the solution? Well, remember we have free variables. So where are our free variables? They're any place we don't have a pivot. And just a quick reminder, we have free variables in this row, in that column, that column, because we have pivots in these two columns. So everywhere we don't have a pivot is a free variable. In this case, we have three free variables. Wow, that was hard to say. 3 free variables, in which case we could write it like this. That should be an x2, not an x squared. So x1 is equal to this. Remember, we solved it looking like this, and then we gave them different names. So we did stuff like, I'm just going to take it back. So let me clear this. So remember, then we said, okay, x1 is equal to x2 plus 4x4 minus x5. So we got something like this, where if I made x2r and x4s and x5t, we got it looking like this. So x1, there should be a 4 right there. All right, so if we do that, apologize, I just realized there was that mistake. So this should be a 4 right here in front of this. So if I have this, then the question that we have is what's the solution set? Well, the solution then is this. Again, that should be a 4. If we do that, notice we have a linear combination of these vectors is any solution because R, S, and T can be anything. Thus, this set of vectors is going to be what we're going to talk about. So this is how linear combination applies to homogeneous systems. And this actually gets us into one of the key fundamental subspaces of a matrix. So if you give me any matrix, by the way, it does not have to be square. Any matrix, there are 4 fundamental spaces we talk about. One is called the null space. This is the one that we just kind of actually looked at. Then we have the column space, the row space, and finally the left null space. All right, now if you look in your book is going to focus on these 3. And I'll be honest, that's all you're going to be tested on. But this one, I think it's still valuable because it'll explain some of the stuff that we've already done in the class and some of its benefits. Because the left null space actually does have a value. So what exactly are these spaces? Let's start with the null space. The null space, where we denote as n of m, is simply the solution set of all the homogeneous system mx. So it's all the x's, it's all the vectors x, such that this is true. Well, that can be just, notice this is always non-empty, by the way, because this always will have at least the 0 vector in it. So a couple things about it. We denote this as the span of vectors. Remember, a span is a set of vectors that covers everything. And we actually have a theorem, the null space of an m by n matrix is a subspace of Rn. So there's at most n set of vectors that need to be in its subset. All right, so also if we're talking about a linear transformation, the null space is called the kernel. It's all the vectors that are sent to the 0 vector in my target space. All right, so the column space, notice C of M, is the set of all linear combinations of the columns of A. So this, if we're looking at all the columns and saying, what is the linear combination of all these? So again, we denote it as a span of a set of vectors. And this is a subspace of Rm. Now wait a second. So the null space is a subspace of Rn and the column space of Rm. I don't have any real trick other than column has an m in it and null does not. Null has an n. So that's the only way that I can tell you that, except that column also has an n. So, you know, I don't know if that helps. Now, another interesting thing is the range of the linear transformation with m is actually the column space. So the column space is the range of the linear transformation. So again, this is how we have it affected if we're talking about the linear transformation. The column space is the range and the null space is the kernel. All right, and also, this is just a quick reminder to make this more clear. This is literally saying, so what vectors B, is there a solution? A solution, we don't care. Now, obviously, since 0 always has a solution, 0 is always in the column space. So again, it's always non-empty. All right, now what about the row space? Now, this is denoted C of M transpose. Your book likes to use an R. Mathematicians do not like that. R of M actually means something else. So I don't know why your book uses some strange notation. Now this space is a set of all linear combinations of the rows. Now, let's pause for a minute and think about why do we care about that? Again, it's a span, by the way. And this is a matrix of subspace of Rn, and interesting enough, one thing about this is it's of the transpose. It's a column space of the transpose, which actually means it's all the vectors B such that xm has a solution. So I forgot to write that in. That's actually what we're looking at. So we're really looking, because when I transpose, if I transpose both sides, you get B transpose is equal to M transpose X transpose. Because remember, transpose switches the operations. So again, this is how transposes come into useful. So we can think of this as only that we're dealing with the null space and column space, but we're dealing for the matrix and its transpose. And as a result, what about the transpose, the null space of the transpose? Well, that is actually the left null space. So left null space is the null space of the transpose of the matrix. Again, so it's this, and it's usually denoted as a span of vectors. Now the null space of M by N is Rm. So you'll notice, wait a second, the left null space and the column space both live in Rm. The row space and the null space both live in Rn. So that's how these things end up actually being complements, and we'll get to a really cool theorem in one of our future sections that further shows how these are related. So let me give you some examples of these different spaces and how we can find them. So let's consider this matrix right here. We want to find the 4 fundamental subspaces. What I'm going to do that is I'm just going to do row reduction. So if I reduce this matrix, it's going to reduce into this. And you can believe me on that, or you can double check. Either one's okay. All right, but if we've reduced this, this new reduced matrix is actually going to be the key that we're going to use to find 3 of our 4 matrix. 4 of our subspaces. So what we're going to do is let's swap over, and I'm just going to put here, if you did the row reduction. Now remember, way back when I mentioned that row reduction simply is like multiplying by a matrix or a set of elementary matrices that we've multiplied. If you multiply all those elementary matrices, you get this, and that's actually going to turn out to be valuable. So this right here is our original matrix, M. This is the row reduced form of M. So what we're going to do then is we simply have to say, what's the column space? To find the column space, we come back here and we say, sorry, I'm going to hit the highlighter. I'm going to highlight the columns that have pivots. And then I find those columns in the original matrix. Those columns in the original matrix are the basis of the column space. Now, quick note, do not use the columns in the row reduced form. Only the columns in the original matrix, because when we did row reduction, we modified columns without using the actual linear combinations of those columns. Thus, we've changed those columns. So you have to use the original matrix, but you look at where the pivot columns are in the original matrix. All right, continuing on though, how about the row space? The row space, again, we look at those pivot columns, but instead of pivot columns, we look at the pivot rows. So what we can do is we can actually take the pivot rows from the original matrix, or we can also take the pivot rows from the matrix over here. So let me erase my rows. So we can, our solutions to this, I point out, are these first 3 rows. That's what I have right here. But you could have just as easily picked these 3 rows right here, and they are also the basis of the column space. The row space. Now notice they are row vectors, not column vectors, and as such, we write them slightly different. Okay, so hopefully that's making sense about what we have. So just to reemphasize, the easiest way to think about it is you can row reduce, find where the pivots are. Pick those columns in the original matrix, and you can also pick those rows in the original matrix for the corresponding spaces. Now, let's clear up this a little bit and talk about the last one, and or the next to last one, that would be this. What about the null space? Well, remember the null space we talked about before being, we just were solving the system of homogeneous equations. So if we took our specific example here, took the row reduced form, and we said, okay, this is a free variable here, we'll call that S. This is a free variable here, and we'll call that T. Then we have x1 is equal to 3s minus t. X2 is equal to negative 2s plus 1/2 t. X3, well, x3 happens to be our free variable, so that's S, and keep going on like that. And then we can, once we get this, remember we can break this up and say, what are our vectors? Well, our vectors in our solution, we have the S vectors, which would be 3, -2, 1, and then 2 zeros below it. Sorry, I went off the screen a little bit. Give myself a little more space for my second one. And the T's are going to be, let's see, that should be -1. The second one has 1/2, 0, or this one is actually 1, and then it's a 1 as well, because it's x5. And these two vectors right here, are the ones that are going to be our basis. So we get this. It's the null space of the reduced format, which, if I clear all this out, you notice is the exact same vectors that I just mentioned. So we can actually work with them to our advantage and kind of figure that out. Now, the last one to mention is, of course, the left null space. Now, there's a couple ways to do it. One, you can literally turn your matrix into the transpose, reduce it, and find its null space. Or the second option is this. Notice that my row of zeros in my reduced is the final row. If we come over here and just pick the row that corresponds in the elementary matrix that reduced my original matrix, that, as it turns out, it should be -1, is actually my left null space. And that's because how you get this last row is this row of vectors times all of this. Remember that row times the original matrix is going to give me my last row over here using our row reduction. And so this is where there's a slight error. Should be a -1 right there. I apologize. -1 right there. So that is how we get our solution in this whole process. I hope that helps you. Please let me know what questions you have, and good luck.